Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to the next session on the subject of system programming with Linux. The title of today's session is Programming the UNIX Named Pipes, also called FIFOs. This slide shows the agenda of today's session. Well, dear students, in the previous session we talked about the pipes. And the biggest disadvantage of pipe was that they have no name and therefore they can't be used between unrelated processes. This limitation was corrected in 1982 with the addition of named pipes in Unix, which are also called FIFOs. FIFOs are like pipes, being stream oriented and half duplex, but has the power to communicate between unrelated processes as well, executing on the same machine. Well, in our operating system concept course, we have seen the uses of FIFOs on the shell. Let us describe it using an illustration. Let's suppose that we have created a special file, a FIFO file on the hard disk, having a name FIFO1. On one terminal, we run the echo program, and the echo program writes a string in this file. So whenever a process tries to write in a FIFO file, the kernel redirects this writing to a kernel buffer inside its own memory created for this FIFO. And whenever a program tries to read a FIFO file from the hard disk, the kernel redirects its reading from the read end of this pipe inside the kernel memory. So a FIFO is just like a pipe inside the kernel memory having a name. So this process, echo, which is unrelated with this process, cat, they both are writing and reading this pipe using this name. So dear students, unlike pipe, which is a pure memory based object and is process persistent, a FIFO name resides on the file system over here, while the kernel buffer associated with the FIFO resides in the memory. So the FIFO data was process persistent, while its name is file system persistent. Let us move on to the Linux terminal and see the proof of this concept. Let me first show you the man page from chapter 7 about FIFO, a special file similar to a pipe except that it is accessed as part of the file system, can be opened by multiple processes for reading and writing. Please do read this man page whenever you have time to have a clear understanding of the working of FIFO. To create a FIFO or a named pipe, we can use the command mkfifo. Let me show you the man page first, mkfifo. And we can always use mknod command to create a pipe. Well, mknod can be used to create different file types. Let me create a FIFO with the mkfifo command. mkfifo, let's suppose FIFO1, and let us create a FIFO using the mknod command, FIFO2, and we have to give the argument p to mknod. Let me show you the long listing of the current working directory. You can see we have two FIFOs, and yes, over here the first character you can see this is the file type, that is a pipe, a named pipe, while these two are regular files. Any program which will try to read or write a FIFO or a named pipe will block unless there is a program writing or reading respectively at the other end. Let me confirm this to you. Let me say echo hello students, and let me write it to to, let's suppose, FIFO1. You see this is blocked. While this is not the case with the regular file, if I write the same contents to a file, let's suppose f1.txt, this will not block. Let me try to read a FIFO, cat, let's suppose FIFO2 for example. So I am blocked. Let me press Ctrl C and let me read a regular file, f1.txt. Do not block. Even if I try to read an empty file, I do not get blocked because there is an end of file character in that file. So remember, reading an empty FIFO is a blocking operation, and writing a FIFO for which there is no reader on the other side is also a blocking operation. Now let us write on the FIFO at one terminal and read it from another terminal. Let me clear screen and let me say echo learning is fun with Arif, and let me redirect this to FIFO1, let's suppose, and let me move on to the other terminal, and over here let me show you the FIFO1. It appears as if this echo processor has written this string inside the FIFO, but over here you see the size of the FIFO is still 0, and this is because actually the writing doesn't go actually on the hard disk. The writing has gone on to this kernel buffer, that is this pipe. Okay, so once again let me show you the writer program is blocked. Let me run a reader program over here that will read from this FIFO1, and it has read the string written by this process. Okay, so that is great. Let's fall back to slides again. Rather, let me show you another example before going back to slides. Move on to this folder. Let me show you a script that says timeserver.sh. Okay, so this is a bash script file that creates a name pipe, a FIFO, and after every 1 second it writes the current date and time in this name pipe, and it do it in a while one loop, a continuous loop, an infinite loop. Let me run this script and let me run it in the background. So it is running. So as per the script, the file in the /temp directory must be existing. Let me check it out. Inside the temp directory, the name of the file is time_FIFO, and the file is there, and the size of the file is 0. And rest assured, the date, the current date is being there in that name pipe. Let me read it for you. Let me read it, this file, temp time FIFO. You see, the date is there, and the date is continuously updated. And if I do like this, you can see it shows you the actual date. That is great. Let me kill this these two servers, 8981, and as well as let me kill 9011. Okay, so far so good. Now I think we all have a fair idea about the use of FIFOs on the shell. Let us fall back to the slides now and see how we can use FIFOs from within a C program. Okay. Well, to create a named pipe or FIFO, you can use the mkfifo library call, which is passed two arguments, the path name and the mode, which is used to set the permission along with the process's umask, and we know that the permission will be mod and not of umask. We can always use the mknod system call to create a FIFO. The first argument to mknod system call is the name of the FIFO we want to create. The second argument is mode. The second argument over here specifies the permissions as well as the file type. Along with the octal mode, we can bitwise order the file type constant. For example, s underscore if reg for creating regular file, s underscore ififo for creating FIFO, s underscore if chr or if blk for character special, block special file, and this for the socket file. Okay, and the third argument is normally set to 0 if you want to create a FIFO file. It is actually used to specify the major and the minor number in case of creating a character and a block special file. Let us move ahead. Okay, so over here we have two unrelated processes, a reader process and a writer process. The writer process opens this FIFO in write mode because it wants to write, and the reader process opens this FIFO in read mode because it wants to read it from here. And this is the PPFDT of the writer process. You see there is one additional entry, that is 3. And this is the PPFDT of the reader process. You can see there is one additional entry, and that is 3, which is a read FD. So remember, this is just a name that is used by this writer and the reader process, two unrelated processes, and all the reading and writing is actually done in this kernel buffer. What is the logic of the program? The writer process will actually get input string from user and write it on the right end of the pipe. The reader process will read those characters from the read end of the pipe and display that string on std out. And this process continues until the writer sends, suppose, an end of file character. Let us move on to the terminal and see the proof of this concept. Let me move on to example 2. Let me show you the writer code first, writer.c. Well, this is a very basic code. I'm using mknod system call to create a FIFO, and then I'm opening that FIFO in write mode because this is a writer process, and then in a while loop I am getting input from the user and writing it to the FIFO. So that is great. Let me move on to the other terminal and show you the, let me change directory to ex2 and show you the code of the reader process now. It's a very similar piece of code. The reader process use the mknod system call to create this FIFO. If it is not already created, then it use the open system call and open this FIFO in read mode only, and then in a while loop it read from this FIFO and display the contents it has read from the name pipe on std out until there is an end of file is received. That is great. Let me compile this reader program, reader.c with the name of reader, and let me compile this writer program with the name of writer. Let me execute this writer program on this terminal, and let me execute this reader program on this terminal. So we have a writer over here, so I need to type some text over here. Learning is fun with Arif. And as soon as I press enter, this content is given to the reader process, and the reader process displays that content. Let me fall back to the writer process again. This is great as well as simple to understand. Let me press enter, and you see the content is displayed over here. And let me send a end of file character by pressing Ctrl D. So the read will return 0 and the program will terminate. That is great. Let us move back again to the slide and talk about bidirectional communication using FIFOs now. Okay. Well, suppose there are two unrelated processes, a teacher process and a student process. And this time both of them want to communicate, so we need two FIFOs. So we have created two FIFOs on the disk, FIFO1 and FIFO2. Both the student and the teacher process has opened both these FIFOs. The student process will open FIFO1 in write mode and open FIFO2 in read mode, while the teacher process will open FIFO1 in read mode and open FIFO2 in write mode. The protocol is that the student is going to write a message in the FIFO1, which will be read by the teacher process, displayed on stdout. The teacher will see what response he or she wants to give. This process will prepare the response and write it on the right end of this FIFO2, which will be read by the student and display on its own stdout. And if you see the PPFTT of both processes, the teacher process has opened two files at descriptor 3 and 4. Similarly, the student process has also opened just two files at 3 and 4. I hope the logic is clear. If it is clear, then let us move on to the terminal again to see the proof of this concept. Let me clear screen, change directory to ex3. Let me show you the teacher program. Okay. So, as I have said before, the teacher program is going to create two FIFOs, one using the mknod system call and the other using the mkfifo library call. Okay. So after doing that, the teacher process will open FIFO1 in read mode, open FIFO2 in write mode. Then it will make a blocking call on FIFO1 from readFD. It will read from FIFO1, write that content on stdout, sleep for 20 seconds, prepare the response and write that message in FIFO2. Well, over here, let me show you the student code, student.c. Well, the student is just going to open the two FIFOs, FIFO1 in write mode and FIFO2 in read mode, as contrary to the teacher's program. The student process will write a message in FIFO1 for the teacher, and then it will read the response from the teacher using FIFO2. And then it will display that message on screen, and finally it is going to delete all the FIFO files that has been created by the teacher process. I think the logic is clear. Let me compile this student program, student.c with the name of student, and let me compile this program teacher.c with the name of teacher. Okay, let me clear screen and let me run /teacher. Well, this teacher program is right now trying to read the FIFO1. The teacher program is trying to read from FIFO1. It is blocked on FIFO1. The teacher program is blocked on FIFO1. Okay, let me come up over here. Let me run the student program. The student program has run and sent a message to the teacher that this program is too difficult to understand. The teacher has read this program, displayed it, read this message, displayed it on stdout, and written a response for the student. And the student is soon going to get the response, yes. And the response is, there is no shortcut to hard work. So we need to work hard. Okay, that is great. That is a great message from a teacher process to a student process. Let us fall back. Okay, so that is all, dear students. That is all for today's session. I think now you all have a very fair idea as to how two unrelated processes can communicate via named pipes. If you have liked it, please subscribe my YouTube channel and share it with your friends. See you next time. Wish you all the best. Happy learning and Allah Hafiz.